following video was produced by Diffusion Incorporated to provide the viewer with a basic history and current state of the biomaterials market for spinal fusion, the importance of immunomodulation relative to the ultimate immune system response, in which rejection leads to fibrous encapsulation of the implant, and acceptance leads to bony ingrowth and ongrowth, and finally presentation of two large-scale animal studies showing statistically significant reduced long-term inflammation and increased bony ongrowth and ingrowth with ZFUZE.
So what is a biomaterial? A biomaterial is any engineered material that is designed to interface with a biologic substance, surface, or being. We use them all the time in spinal surgery. Our screws, implants, interbody cages are all different forms of biomaterials. We're actually in an amazing area of different materials where we can construct them out of a variety of different substrates, shape them the way we want to shape them. In fact, if you look at the market, there are dozens and dozens and dozens of different kinds of interbody cages out there, each made out of a different material, whether it's ceramic, plastic, metal, or human bone. We've taken them and structured them in different ways. We've 3D printed titanium, we've drilled holes in PEEK, we've combined the two. But in the end, it all does the same thing. They hold a space, they do contain bone that we put them in, but the materials themselves do not reliably interact with the bone to create a bone-material interface and fusion. And that's really the next generation of biomaterials for spinal surgery. How do we create something that does the job we want it to based upon the material itself?
Biomaterials have been around and in use for 50, 60 years for a variety of applications. And the primary design criteria for biomaterials has typically been characteristics such as how stiff it is, or how strong it is, or how big the pores are, or what the surface characteristics are like. And all those things are indeed important. But what more and more people are recognizing now is that the primary determinant of clinical success, and by that I mean the response of the patient, involves the patient's immune response. So inflammation actually is now being recognized as having good forms of inflammation and let's call them bad forms of inflammation. And these different inflammatory responses are embodied in cells like macrophages. Macrophages are one of the cells in the body that are part of the inflammatory system, and they used to be thought to be have strictly one job in life, and that is to respond to infectious agents or respond to foreign materials like biomaterials and form capsules around them or foreign body granulomas. Now it's recognized that these very same cells can assume a separate phenotype and be pro-reparative. And the pro-inflammatory version is referred to as an M1 type cell, and the pro-reparative version is referred to as an M2 type cell.
Let's take a closer look at the macrophage response. As seen here, rat monocytes are introduced to conventional hydrophobic PEEK on the left and negatively charged hydrophilic ZFUZE composite on the right. The monocytes initially signal the M1 phenotype, commensurate with normal wound healing and the routine initial inflammatory response to wound or injury. The immune system recognizes hydrophobic materials as foreign contamination since native surfaces within the body are hydrophilic. At day 4, a sudden and drastic shift to an M2 phenotype was observed on the ZFUZE surface. The M2 phenotype signals for anti-inflammatory and cellular repair cytokines such as interleukin-10 and interleukin-12. IL-10 and IL-12 contribute to the maintenance of bone mass through inhibition of osteoclastic bone resorption and upregulation of osteoblastic bone formation. Contrarily, the inert hydrophobic surface of PEEK demonstrated a prolonged M1 inflammatory response along with protracted increases in IL-1 beta and IL-6 cytokines, which are known to contribute to vascularized fibrosis or walling off of a foreign body or implant deemed to be not self or dangerous to the immune system because of its hydrophobic nature. With over 300 biomaterials tested using the same M1 to M2 immunomodulation assays, ZFUZE was the first and only man-made material that consistently demonstrated the ability to shift the M1 to M2 phenotype in a rapid and predictable manner.
Well, the whole M1, M2 story is interesting from a scientific or academic standpoint, but the real relevance comes in what does that mean from a clinical outcome standpoint. And the simple answer is that the more robust and the prolonged that the M1 pro-inflammatory response exists, the more fibrous tissue and dense scar tissue is going to accumulate at the site. What one would really like is a rapid transition from the pro-inflammatory M1 phenotype to the M2 phenotype, which would then minimize fibrosis and facilitate the deposition of site-appropriate types of tissues. By site-appropriate, I mean wherever the implant is placed, the types of tissues that are normally there are the types of tissue that would then be deposited over time.
The extremely hydrophilic surface of ZFUZE alters the surface charge on the implant, resulting in a negative ionic charge. This creates an ideal environment upon implantation to immediately attract and adhere the required precursor proteins for bone growth to the implant surface. The rapid shift at day 4 to M2 macrophage phenotype signals the start of the healing process via early osteoblast proliferation and increased adhesion, accelerating osteogenesis and ultimately supporting long-term osseointegration. Recent results from 2 animal studies provide further support for the immune response and osseointegration findings with ZFUZE.
The functional ovine cervical model was one of the more exciting studies that we were able to conduct in our lab. When we look at the 2 materials, they are essential to understand the biomaterials of choice. We looked at a comparison of peak interbody devices to that of the ZFUZE product line. And when we see the response at the 6-month time point in these sheep, it was astounding to see the immune response of the specific specimens involved in the studies. As a biomarker for inflammatory response, we looked at IL-1 beta as well as IL-6. The interleukins were a great indicator and agreed with Dr. Badylak's work looking at the M1 to M2 conversions. When we look at the IL-1 beta and the amount that it was able to suppress in comparison to that of the response in the peak interbody levels, it was statistically significantly different at the 6-month time point. It was a very exciting outcome for us. The critical size defect model, we were able to look at the difference in on-growth versus in-growth. These are 2 different healing responses that the bone implant interface utilizes in order to ensure the best material and ultimate healing response for these type of devices. By differentiating what was known as in-growth versus that of on-growth, we're really better able to understand what these devices will do in the human body. And we were able to, again, on both levels, that's in-growth and on-growth, to detect a statistically significant difference between that of the ZFUZE product line in this critical defect size model versus that of the peak interbody cages. The red rendering that you see represents the peak material. The peak material, the de facto standard used in some of the spinal interbody devices, you can clearly see the amount of on-growth and the limited amount of on-growth when you compare that to the ZFUZE-based product, which is colored green in these renderings. In comparison, you'll see that statistically significant on-growth, but you'll also notice a statistically significant difference in in-growth. That's the amount of bone that was able to fill into the void. So when we look at the red model, the peak control, versus that of the ZFUZE-based model, the green model, you'll see that in both counts, the on-growth and the in-growth are statistically significant when we use this bone mineralization index in comparing these 2 healing mechanisms to that of the standard peak device. The ZFUZE clearly represents an advantage regardless of the healing mechanism. Again, a very exciting area for us as we look at these 2 very aggressive animal models in trying to discern what makes ZFUZE and how ZFUZE is better than of the de facto standard PEEK.
ZFUZE is the first load-bearing biomaterial engineered from the bottom up for orthopedic applications. In addition to demonstrating early cellular adhesion and proliferation, ZFUZE has shown an early switch to the healing, pro-reparative phase of the immune response that we now understand is critical for building bone and avoiding fibrous encapsulation that occurs with prolonged inflammation. And ultimately, the animal study work done to date shows exciting promise for long-term osseointegration with ZFUZE. Not only does the ZFUZE composite offer a completely new biomaterial, but it also provides a long-term R&D platform for future therapeutic polymers.